6. A summary of curve sketching, day 2. Right? So in review, curve sketching. 3 things you want to do. First, determine domain and range. Right? What makes the bottom 0? That ties to your domain. Look for limits at infinity to determine your range. Right? Next, look for intercepts and asymptotes. And again, domain and range are tied to your asymptotes. Your intercepts, what makes the top of a rational 0. For the x-intercepts, for the y-intercepts, just plug in 0 for x. And finally, step 3, whole bunch of wording, sums down to make a sign chart. Okay? Make a sign chart focusing on increasing, decreasing, concave up, concave down, inflection points, relative extremum. Right? So let's do a problem. Remember, to facilitate this, I'm going to make the sign chart for you. The focus is just on interpretation. And that is very similar to what they do in the AP exam. Right? So here's our function. F of x equals x over the square root of x squared plus 2. Because this is x over the square root of x squared plus 2, to find our asymptotes, our horizontal asymptotes, we need to approach both infinity and negative infinity. Because that square root's going to mess things up. As we approach infinity, we got 1. As we approach negative infinity, we got negative 1. There's no way the bottom can be 0 because we're squaring something and adding 2. For x-intercepts, if you plug 0 in, you get 0 over the square root of 2, which is 0. And then what makes the top 0 for the y-intercepts is 0. So the intercepts are 0, 0. And then our critical numbers, no critical number from f, meaning it's always increasing or decreasing. And for the second derivative, critical number at 0. We can see we have a relative max at 0 because the sign changes from positive to negative. So as we graph this, no, that's an inflection point. Sorry, because it's the second derivative. We can see we have an inflection point at 0, 0 because the second derivative changes signs from positive to negative. So it's going to be concave up beforehand, concave down afterwards. So let's sketch this. And again, I'll split the screen so we have the information for the sign chart, and we have a graph we can apply it to. So we'll start by drawing in our asymptotes. As we approach infinity, we approach 1. I'm going to scale this to be 0.25 so that we got a little bit more information as we look at this. Otherwise, it's all going to pinch down and be really hard to see. So as we approach infinity, our graph approaches 1. As we approach negative infinity, our graph approaches negative 1. All right? The important point here, our inflection point is 0, 0. We got an inflection point here. Before the inflection point, we're concave up and increasing. The concave up shape looks like that, and the increasing part is there. So we need to do our concave up into our inflection point. After our inflection point, we're concave down and increasing. Concave down is a frown, and the increasing part is right there. So we need to make that shape on the way out of our inflection point. We can see our graph there through our inflection point. And remember to keep your graph, your slope increasing, your slope positive through it. So you don't get a horizontal or a vertical tangent. There's our graph. Using our sign chart, our intercepts, and our asymptotes. Let's look at this another way. All right? We've done it a lot numerically, analytically. Let's look at it graphically. So given the graph of f prime, sketch the graph of f. Hint, there's more than one correct answer. We're just going to look for one. And I'll discuss briefly why there's more than one correct answer as we look at this. So, first off, there's an asymptote in the derivative. There's an asymptote in the function. All right? On the right side of the asymptote, our derivative is positive. Right? Our derivative is positive, so that means over here our function is increasing. On the left side of the asymptote, less than 0, our derivative is negative, so our function is decreasing. If you want to look at it a little bit further, here our function is decreasing. Our function is decreasing, that means its derivative is negative. The derivative of the first derivative tells us concavity. So this is decreasing, which means our second derivative is negative, which means this is concave down. Over here, right here, that's decreasing. If our derivative is decreasing, our second derivative is negative, so the function is concave down again. So what we got here is decreasing, concave down when x is less than 0, increasing, concave down when x is greater than 0. I'm going to lock everything in place. So the concave down shape is right here. The decreasing portion is right there. So we got that graph right there. Increasing concave down is right here. Increasing concave down is right there. Now, that's one possible graph. What are the other ones? They're not really difficult to get. Just shift up or down. Any one of these values follows the rule, increasing concave down or decreasing concave down in the correct intervals. You just shift up or down, and those would be the possible ones. You just need to give one. It doesn't matter where. So right there, why not? Okay, here we have f prime again. Graph f. So again, let's look at the critical numbers. The critical numbers is where the first derivative is 0. So right there, the first derivative is 0. It's going to be a horizontal tangent when x equals 0. We're negative coming in to x equals 0. Negative means the function is decreasing. The derivative is positive coming out of 0. So that means the function is increasing. So our function is going to look like that. And we can see our derivative is increasing the whole way. That means it's always concave up, because when the derivative is increasing, the second derivative is positive, which means concave up. We can see we have a relative min here because we switched the derivative from negative to positive. Right? So you're given the same information, you just kind of got to evaluate it a little bit differently when you're given a graph. Look for the critical numbers where it's 0 and then check positive or negative to see if the function is increasing or decreasing. Right? Same graph, but now it's the second derivative. All right? So what we can see here is we have an inflection point. You might be able to sit back and say, okay, last time I did this, I graphed this. Well, that would be our first derivative. Right? So we can see that right here is an inflection point. This would be concave up to the right of the inflection point. the left of the inflection point will be concave down. All right? Using what I kind of sketched as a derivative, we can see this graph could always be increasing. And I say could because there's more than one correct answer. I'm going to use this as my derivative so that that's my more than one correct answer will be based off of that. Right? So it's always concave, or it's concave up to the right, concave down to the left, but it's always increasing. Okay, the concave down shape is right here. This is the increasing component. Concave up shape is right here. This is the increasing component. There is one possible graph for F. All right, so finally, let's graph this one. This is our derivative. We can see our critical number is right here at 0. We can see we're positive afterwards, so it's increasing. Up until 1, the derivative is increasing, so it's concave up and increasing till 1. Concave up and increasing. Afterwards, it's constant, meaning the concavity doesn't change. It'll just be linear. All right, right here, we're decreasing. Concave up. Still 1. And it's linear afterwards. Linear with a slope of 2. With a slope of 2. There we go. That's one possible F. And again, to get other ones, you shift it up or down. So in conclusion, domain and range. Intercepts and asymptotes. And then make a side chart. Evaluating increasing, decreasing, concave up, concave down, relative extrema, and inflection.